Okay, so the problem I got this week was problem number 68. Pretty much it's a system like this where it has two parallel bars next to each other and has a bar resting on top of it with some mass M and some length L. It's in a magnetic field like this, and it's a two-part question. The first part is asking what direction the current is going to be going in to give this bar on top here a force to the right. So we can find that out by consulting what force is due to a magnetic field. So we have a cross product, force equals IL cross B. The L and the B are vectors, and the force is a vector as well. So pretty much we just consult our right-hand rule to figure out what this current is going to be. Current's going to be our first finger, which we don't know. Middle finger is going to be the B field, the magnetic field, and the what it equals is our thumb. So this is pretty much what we're given. Our force, we want to go to the right. Okay. The middle finger is going to be our beta. So we're going to give it a little. That's what that's going to look like. And what is our finger going to be doing? According to the right-hand rule, finger is going to be going, because we have the magnetic field going up, the force to the right. Where's our finger pointing? It's pointing into the page. So if we orient it like that, it's going that way. That's the direction of the current. That's where our eye is going. Okay, so that's part A. It's pretty easy. It's just a little application of the right-hand rule. Part B is where you have to use a little bit more. You have to use some kinematics and Newton's second law. And pretty much what it's asking is we apply a current to this thing, and it's in a magnetic field, and from the previous part we know it's going to have a force. Those two things are going to cause a force to the right. What the question is asking is what's the final speed as it leaves this point right here. So we're going to have to, like I said, we're going to have to use some force, and we're going to have to use some Newton's second law. We're going to have to use some kinematics. So first thing, let's find the force. So the force, we have it written right here, is the IL cross B. We can simplify that a little bit to get rid of that cross product. So the F is going to equal IL B sine theta. It's just that's what the cross product equals. It's just the magnitude of the vectors times the sine of theta. And as you can see in here, this is our L. It's same thing, these two L's. It's L. Angle between them is going to be 90. We all know that when you have the sine of 90, it's just 1. So our force equals ILB. Not too bad. We also know from previous classes that force equals mass times acceleration. It's just Newton's second law. So these two are going to equal each other. ILB equals mass times acceleration. Divide the mass over, and we got our acceleration. Okay, now once we have our acceleration, we can plug it into our kinematics equation. There's 3 of them, but we're just going to use one. And this is the one you're going to want to use. Final velocity squared equals initial velocity squared plus 2ax. And actually, we're not going to be using x, the distance that's traveled. We're just going to be using the d, because that's the distance it's traveling. from the start to the end, the final velocity we were wanting. So we're going to use d. We know that this bar up here starts from rest, so its initial velocity is going to be 0. Its acceleration we just solved for. It's this stuff right here. So pretty much plug the acceleration into our equation and solve for v, and we got our final speed. So v final squared equals 2 I, oops, it's not an ILB over m times d. 2AIL. Okay, so then we just take a square root of that, and we got our expression for the speed. Speed equals the square root 2ILB d over m. That's our answer. Well, that's it. That's how you find the speed, and that's how you find the direction of the current in problem 68.